Assalamualaikum everyone, I hope you guys are doing well. So in this video, we are going to be looking into type 6 of permutations, and type 6 is where you have to arrange objects, and you have to not just arrange them in a straight line, but you have to arrange them in different rows and different columns. Now, these kind of questions are not very common. In fact, I think so far there have only been 5-6 questions, and we're going to solve 5 of those questions. And a lot of the questions are very similar. I mean, they're done the same way that you would do when you're arranging them in a straight line, but there are a few questions in which you have to watch out for some small technicalities. So let's find out what those technicalities are, and let's start with the first question, which is a very old question. It's from October-November 2002, question paper 6 and question 4. Okay, let's see what it says. So it says here, in a certain hotel, the lock on the door to each room can be opened by inserting a key card. If you've been to a hotel, if you've ever stayed in a hotel, you know how that works. The key card can be inserted only one way around. The card has a pattern of holes punched in it. The card has 4 columns, and each column can have either 1 hole, 2 holes, 3 holes, or 4 holes punched in it. You can see that from the diagram. Each column has 8 different positions for the holes. The diagram illustrates one particular key card with 3 holes punched in the first column, 3 in the second, 1 in the third, and 2 in the fourth. Okay. Now, show that the number of different ways in which a column could have exactly 2 holes is 28. Now, this is actually a part which is not related to permutations, so I'm going to skip this. In fact, the parts that we're going to deal with will be part 2 and part 3. So let's see what part 2 says. Part 2 says, find how many different patterns of holes can be punched in a column. Okay, so if you look at a column, notice that we have 8 places, okay? And in these 8, let's call them blocks, okay? In these 8 blocks, we can either have 1 or 2 or 3 or 4 holes, and each hole is identical, okay? So since we're talking about identical objects, remember what happens when you're arranging identical objects? You have to divide by the number of factorial as well, okay? So let's basically draw one column. So here's one column, 1, 2, 3, 4, 5, 6, 7, 8. Okay, so in this column, if let's say there is to be 1 hole, that means we have how many options for that? We have 8 options for that. So that means if we're talking about 1 hole, so we have 8 options for that. Now, the question earlier said, make sure you read the question very carefully. So the question said can either have 1 hole, 2 holes, 3 holes, or 4 holes. So that means it's not necessary that every column is going to have 1 hole. A column can also have 2 holes. So how can I have 2 holes in this column where we have 8 spaces? So the way that we can do that is 8p2. Why? Because think of it this way, that we have to arrange 2 objects and we have 8 different places to do that. But the 2 objects that we're arranging, this is the technical part. The 2 objects that we're arranging are identical. Okay, why? Because if I punch 2 holes, now these 2 holes are identical. So that means if I swap places of these 2 holes, nobody would be able to tell the difference. Why? Once again, because they're identical. So how do we take that into account? We take that into account by dividing by 2 factorial. Now, it is possible, as the question said, that you can have 3 holes per column as well. So that means that can be done 8p3 number of ways. And because we're talking about 3 holes and the 3 holes are identical, we will have to divide by 3 factorial. Now, another possibility is 8p4, and once again, because we're talking about 4 identical holes, we have to divide by 4 factorial as well. So how does this work? Let's see. Let's find out 8p2 divided by 2, which is equal to 28. So 8 plus 28 plus, let's find out 8p3 divided by 3 factorial, that's equal to 56. Now let's find this out. 8p4 divided by 4 factorial, so we have 70. So that means in one particular column, there are how many possibilities? There are how many different patterns of holes can there be? 8 plus 28 plus 56 plus 70, that's equal to 162. So this is basically the number of different patterns that you can have in one column only. Okay, so that's the answer to part 2. Now let's talk about part 3. Part 3 says how many different possible key cards are there? Okay. So think of it this way. Let's say you're tossing a coin 3 times, and you want to find out how many total number of outcomes, how many different number of total outcomes can there be. So if you toss a coin the first time, there are 2 possible outcomes. If you toss a coin 2 times, so you'll multiply it by 2 because you have the same number of outcomes in the second toss as well. And if you're tossing it 3 times, that means you'd multiply it by 2 again, because every time you toss a coin, there are 2 possible outcomes, 2 different outcomes. So altogether, if you're tossing it 3 times, that means you have 2 to the power of 3 or 2 times 2 times 2, which either way is equal to 8. So these are the number of different outcomes that you can have. Now here, we are talking about a card, okay? Now this card has how many columns? This card has 4 columns. Now, as far as the first column is concerned, in the first column, we can have 162 different outcomes. That means we can have 162 different patterns. And the same is true for every other column, okay? Because the question didn't say that column 1 will have 1 hole or column 2 will have 2 holes. In any of the columns, you can have 1, 2, 3, or 4 holes. So altogether, there are 162 different patterns per column. And how many columns do we have in one card? We have 4 columns. That means we'll do 162 times 162 times 162 times 162, or simply 162 raised to the power of 4, which is going to give you a freakishly large answer. Let's see what that is. 162 raised to the power of 4. Okay, so this is 7,233,94816. So let's see what that is. That's 723,394,816. But we're talking about keys, so the more the number of different outcomes you have, the less likely they can be replicated, and that just enhances the security. So that's I hope you guys have understood this question. It was a tricky one, no doubt about that. Now let's move on to the next question. Let's see what this says. So it says here, the diagram shows the seating plan for passengers in a minibus, which has 17 seats arranged in 4 rows. The back row has 5 seats, and the other 3 rows have 2 seats each on the side. Once again, you can see the diagram. You'll understand how it works. 11 passengers get on the minibus. How many possible seating arrangements are there for the 11 passengers? So as far as the first part is concerned, we have 17 different seats. So can we have 11 different passengers? We want to find out how many ways we can arrange them. And that's pretty simple. That's just going to be 17p11. Let's see what that is. 17p11. Okay. This is an answer which is in standard form. So we'll write 4.94 into 10 to the power of 11. Okay. Now, let's talk about part 2. Part 2 says, how many possible seating arrangements are there if 5 particular people sit in the back row? So that means in this back row, there are supposed to be 5 specific people, 5 particular people. So let's see how we can do that. Remember, whenever there's a restriction, we have to settle that restriction first. So if you're starting from here, if we're starting from, let's say, the leftmost side, so we have 5 options for the first seat, which is at the very back. And then we have 4 options, and then we have 3 options, and then 2, and then 1. And that's it. There's no other way this can be done. You have basically 5 seats and 5 people who are going to sit on these 5 seats. So you could either do 5p5 or 5 factorial. So that means for the 5 people who are going to sit in the back row, it's 5 factorial. Now, if you think about it, there were 17 seats. Now, from the 17 seats, 5 are already occupied. So that means now we're down to 12. There were 11 people who are supposed to get on the minibus. Now 5 have already taken their seats. So that means now we have to arrange 6 of them. And the way we're going to do that is simply 12p6. Let's work this out, see what the answer is. 5 factorial into 12p6. And that's equal to 79833,600. So that's 79,833,600, which is the correct answer. Okay, now question number 3. A builder is planning to build 12 houses along one side of the road. He will build 2 houses in style A, 2 houses in style B, 3 houses in style C, 4 houses in style D, and 1 house in style E. Find the number of possible arrangements of these 12 houses. Okay, so first part, very simple. We have 12 houses, but not all 12 of them are unique. There are some identical ones as well. Okay, so let's consider those. So there are 2 houses that are going to be in style A, so we need to divide by 2 factorial. 2 houses in style B. Make sure you're reading the question carefully. So we've considered 2 houses in style A and in style B. Now there will be 3 houses in style C, 4 houses in style D, and that's it. You could go ahead and divide by 1 factorial, but that's really not going to make a difference. So let's work this out. 12 factorial divided by 2 factorial is as good as 2, so you don't need to write 2 factorial. 3 factorial is 6. And 4 factorial is 24. So if you remember these factorials, instead of typing 2 keys, you'll just have to type a 1. So we're looking at 831,600. That's the answer to the first part. And like I said in the beginning, that some questions are pretty much the same way, done the same way that you would do when you're arranging them in a straight line. Okay, then the question says, now there is a small misprint, which I should mention. Okay, the question starts from here. The 12 houses will be in 2 groups of 6. Okay, see diagram. Find the number of possible arrangements if all the houses in style A and D are in the first group, and if all the houses in styles B and C and E are in the second group. Okay, so let's drag this here. So let's talk about the first group. Now remember, there are 6 houses per group. 1, 2, 3, 4, 5, 6. Okay, so when we're talking about the first group, according to the question, there are going to be, if all the houses in styles A and D are in the first group. Okay, so how many style A houses do we have? We have 2 style A houses. And how many style D houses do we have? We have 4 style D houses. Okay, so how many ways can you arrange 6 objects? You can do that 6 factorial number of ways. Now, of these 6, there are 2 that are identical and the other 4 are also identical. So that means we'll have to divide by 2 factorial into 4 factorial. Okay, so let's work this out. See what do we get. 6 factorial divided by 2 factorial into 4 factorial. Let's see what that is. That's equal to 15. Okay, so let's hold on to this. Now let's talk about, so I'm going to call this, okay, let's not call it group A. This is the first group. Now let's talk about the second group. So once again, in the second group, there are an equal number of houses. Okay, but in this group, in the second group, we have all of style B, C, and E. So that means in this group, let's go back to the question. There are 2 houses in style B. Okay, there are 3 houses in style C, and there's only 1 house in style E. Okay, so how many ways can you arrange 6 objects? 6 factorial, but among these 6, there are 2 that are identical and 3 also that are identical. So let's work this out, see what do we get. So we get 6 factorial over 2 into 3 factorial, which is 6. That's equal to 60, okay? So how many options do we have, or how many different arrangements do we have in the first group? That's 15. And how many arrangements do we have in the second group? That's 60. So that means altogether, there can be 15 times 60, which is equal to 900 different ways that the builder can arrange these houses, okay? So that's it. That's the answer to this question. Now let's move on. I believe this is it's the second to last question. Let's see what this says. So it says a group of 8 friends travel. Okay, this is one of my favorite questions, actually. Not just this part, but this question altogether, because it has a bit of permutations in it as well, which, by the way, I should mention we are not going to cover. So this part we are going to ignore, okay? We're going to cover permutations in separate series of videos, inshallah. A group of 8 friends travel to the airport in 2 taxis, P and Q. Each taxi can take 4 passengers. All right, now we have the taxi diagram as well. Each taxi can take 1 passenger in the front and 3 passengers in the back. See diagram, okay. Mark sits in the front of taxi P. John and Sarah sit in the back of taxi P next to each other. Okay, so we have to keep that restriction in mind. Find the number of different seating arrangements that are now possible for the 8 friends. Okay, so let's start with taxi P, since that's where the restriction is. Now, John is going to sit in the front. So that means as far as the front seat of taxi P is concerned, there's just one option. Okay, there's only one John, so just one option. Mark. Mark is going to sit in the front of taxi P. So since there's only one Mark, that means we just have one option. Okay. Now let's talk about John and Sarah, who are going to sit together. Now, what do we do when 2 objects are to be kept together? They can shuffle amongst themselves. Okay, and if they want to shuffle amongst themselves, they can do that 2 factorial number of ways. Now, who's going to sit? Who's going to be the 4th passenger in taxi P? Remember, there were 8 friends. Mark is sitting in taxi P. John and Sarah are sitting in taxi P as well. So 8 minus 3, 5. That means now there are 5 friends left. And one of those 5 friends are going to now be the 4th passenger in taxi P. So that means we have 5 options as far as the 4th passenger in taxi P is concerned. So 2 factorial. Now don't forget that this 4th person and John and Sarah combined can shuffle amongst themselves 2 factorial number of ways. Okay, the question does not say that you should have John and Sarah first and then Mark, or it could be the other way around. Okay, something we did when we were doing type 2. Yeah. And remember that for the 4th passenger, we have 5 options. Now, as far as taxi Q is concerned, that's pretty straightforward. There are 4 passengers left and all 4 of them have to sit somewhere. So that means that can be done 4 factorial number of ways. Okay, so you can think of it this way, that you have 4 options for this seat, 3 for this, 2 for this, and 1 for this. So let's find out. Let's see how many different seating arrangements are there. 2 factorial times 2 factorial times 5 multiplied by 4 factorial, which is equal to 480. And there you go. That's it. That's the answer. Okay. Next question. So this question says, a village hall has seats for 40 people consisting of 8 rows with 5 seats in each row. Mary, Ahmed, Wayne, Elsie, and John are first to arrive in the village hall and no seats are taken before they arrive. How many possible arrangements are there of seating Mary, Ahmed, Wayne, Elsie, and John if assuming there are no restrictions? Okay, now let's solve question number 5. Let's see what this says. A village hall has seats for 40 people consisting of 8 rows with 5 seats in each row. Mary, Ahmed, Wayne, Elsie, and John are the first to arrive in the village hall and no seats are taken before they arrive. How many possible arrangements are there of seating Mary, Ahmed, Wayne, Elsie, and John, assuming there are no restrictions? Okay, so the first part is usually without any restrictions, but before we solve the first part, it's very important that we understand the seating arrangement that the question is talking about. So there are the seating arrangement is for 40 people and there are 8 rows with 5 seats in each row. So that means this is what it looks like. So you have row 1, row 2, row 3 with 5 seats, row 4 with 5 seats, and you have, like these, you have how many rows? You have 8 rows. Okay, so that means this is what the seating arrangement looks like. Okay, now we're doing the first part. In the first part, we have 40 spaces, right? So that's 40. And we have to arrange how many people? We have to arrange, let's count. So 1, 2, 3, 4, and 5. So we have to arrange 5 people and we have room for 40. And the way we can do that is simply 40p5. So let's do that. 40p5 is equals to 78,960,960. Okay, so this is 78,960,960. Yeah, okay, that's an interesting number. Okay, now part 2. Part 2, once again, one of my favorite questions. How many possible arrangements are there of seating Mary, Ahmed, Wayne, Elsie, and John? Okay, now here are 2 different restrictions, okay? If Mary and Ahmed sit together in the front row, okay, so first let's talk about this. First, let's talk about how Mary and Ahmed can sit together in the front row. In fact, let's read the question and then we'll deal with this separately. And the other 3 sit together. So let's underline this also. The other 3 sit together in one of the other rows. Okay, so that means in which row? It can be in any one of the remaining rows, any one of the 7 rows, but the other 3 must also sit together. So 2 people must sit together in the front row and the remaining 3 people must sit together in the remaining 7 rows. Okay, so let's talk about the first restriction where Mary and Ahmed are supposed to sit together. Okay, so they can say, if they want to sit together, we will put them in a box and they can shuffle amongst themselves 2 factorial number of ways. Okay, now 1, 2, 3, 4. We have 4 different units, so we'll multiply it by 4 factorial. But although I said 4 different, but they're not all different because the blank spaces are identical. So that means I need to divide it by 3 factorial. Okay, if let's say there were people in these blank spaces, then we wouldn't have divided by 3 factorial. But because these blank spaces are empty, we have to divide by 3 factorial. Okay, so this is basically the first restriction, which is kind of easy to deal with. Now let's talk about the second restriction. Now, in the second restriction, it says that the other 3 sit together in one of the other rows. Okay, so let's drag this down so we have room. Now we're talking about the remaining 7 rows. Now, in this remaining 7 rows, 3 people are to sit together. And who are they? They are basically Wayne, Elsie, and John. Doesn't matter who they are, they're just 3 people, okay? So once again, these 3 people can shuffle amongst themselves 3 factorial number of ways, okay? And multiplied by, we have 3 units that we're supposed to arrange. So 3 factorial, but of these 3 units, 2 are identical because we have 2 blank spaces. Nobody's going to sit here. So this is basically how they can arrange themselves in one row, okay? But the question does not say that they're going to sit in the row that is right behind Mary and Ahmed. So if you think about it, they have how many rows to choose? They have 1, 2, 3, 4, 5, 6, and 7. So they have 7 rows to choose from. So that means this, whatever this is equal to, this will be multiplied by 7 because this is for one row and there are 7 different rows to choose from. So that means whatever options they have for one row, they have for the remaining 7 rows. They have that for basically all of the remaining rows, and there are a total of 7 rows. So altogether, they can arrange themselves. Let's find out how many number of ways. So 2 factorial multiplied by 4 factorial divided by 3 factorial is as good as 4. So 8 times 3 factorial multiplied by 3 factorial divided by 2 factorial is as good as 3 factorial multiplied by 3. So let's do that. 3 factorial multiplied by 3 multiplied by 7. So that's 126. So 8 is the number of ways that Mary and Ahmed can sit together. 126 are the number of ways the 3 remaining people, Wayne, Elsie, and John, can sit together in any one of the remaining 7 rows. So if we multiply this, let's see what we get into 8. So we get 1008. So there are 1008 number of different ways in which this restriction can be fulfilled. So that's it. That's all there is. These are the questions where you had to arrange objects in different rows and columns. I hope this concept is also now clear. There's only one category that's left, and that is how permutations apply to numbers. So that's what we're going to do, inshallah, in the next video. That's it for this one. I'll see you in the next one. Until then, take care. Bye-bye.